Swayamprabha. Digital India. Educated India.
Good morning. Let us continue our discussion of drop and velocity size distributions as applicable to sprays. Okay, we are going to define these distributions in the X V space. Where x is the drop size and x is any number between 0 to infinity. Okay, it is a positive number, and v is, we will just stick to one component of velocity, and because the component of velocity can be either positive or negative, it goes between minus infinity to infinity. Those are, I mean, without knowing anything about a given spray, this is sort of the limits I can set on it, right. So, now I define a function f in these two variables. F of x comma v is a probability density function if it satisfies two properties. One, f of x comma v is greater than 0 for all x and v. That are admissible. And the second condition is simply that if I was to integrate the probability density function over the set of limits, that has to add up to 1. And just to recap, this second condition comes from our basic definition of a probability density function, that f of x comma v times dx dv is the actual probability that is the size of the drop falls in this range x to x plus dx, and okay. So, if f of x comma v is a probability density function, this probability density function multiplied by dx and dv. So, if you imagine x and v as being two orthogonal axes describing this x v space, dx comma dv is like a tiny area, elemental area in this space. Probability density function at that point x v multiplied by that elemental area gives me the actual probability that a drop falls at that point. Okay. Now, if I add up these actual probabilities over the entire range of admissible values of x and v, that is supposed to add up to 1. That is our law of simple law of probability, right. Okay. Now, just to set things in perspective, if I take a spray, I have a spray nozzle that has got this spray. I have, in the most general description, 3 spatial coordinates describing this spray. So, if I draw an axis, there is a radial, if I just use cylindrical polar coordinates, there is a theta and there may be a z coordinate. So, I have an r, theta and z describing this. So, if this is my origin point, every point in the spray has a position vector I will write it more compactly. In just coordinate notation, that is easier. Okay, so, this is a position vector in 3 coordinates, and in each of these 3 coordinates, the velocity vector may have a v r, v theta, v z, and if I simply take the size, and if I say size is one scalar quantity that describes the physical measure of the volume in the drop, and t is time. So, if I take a very simple unsteady spray, at every point P, the point P itself is described by r, theta and z, its spatial coordinates. At that point, I have a probability density function in x, v r, v theta and v z. So, the PDF is essentially a function in x, v r, v theta, v z. These are the arguments of the probability density function. Okay, so, if I integrate it appropriately over these 4 independent parameters, independent coordinates, now the space in which the spray is characterized is this x, v r, v theta, v z space, okay, and the physical space is r, theta, z and time. I use a semicolon to separate the list of arguments in the PDF So, list of arguments, I will say describing the PDF space, or in which the PDF space is this would be the most complete description of a spray. If I can come up with this function f, that is going to tell me the probability density of finding a given size of drop with a given set of velocity components at a given physical point in the space and at a given point in time. I can, as time varies, at that same physical point in space, the PDF could evolve if I have a real unsteady spray, right. Simplest case, let us say a diesel injector puts out large drops in the beginning of the injection cycle and large drops at the end of the injection cycle. In the middle there you may have a real fine atomization. So, this f at one point sees a variation in time, and even if I take a steady spray like the one we saw in the video earlier, at different points in the spray I will have a different probability density function in the size coordinate and the velocity coordinate. So, just to set, we started to talk of f of x comma v as a probability density function in this 2 parameter space. Okay. What we really should be looking at is a probability density function in the 4 parameter space of x, v r, v theta, v z that itself varies as a function of r theta z and time. This is like the most general description we can think of, okay, in a statistical sense. So, we are still looking at the moment we say probability density, we are suggesting that there is in some sense a local stationarity over some period of time or over some ensembles of cycles. Okay. We will look at that when we look at experimental techniques, because we will take advantage of this in making some measurements of these sprays. Okay. But this is our understanding of what it is. So, let us now go back to, now I do not want to sort of, so just to understand what the most complicated way of looking at a spray, but we will simplify it just to understand some of the physics of these distributions. Okay, we said integral this is just coming from the idea of probability. Okay. Now, if f x comma v dx is the probability of any velocity, right. So, this here is a function of velocity. If I perform this integration from 0 to infinity, this becomes, I will put this in curly braces, so I want to see if I can define like a mean velocity. I want to find a mean drop size in this thing. So, let us first simplify this. If I define a mean drop size, x times f of x comma v dx dv integrated from 0 to infinity and the v integral going minus infinity to infinity. This gives me the mean drop size over all the velocities. Okay. What I want is a mean drop size of all the drops that are moving with some velocity v to v plus dv, let us say. Okay. So, if I ask myself the question, what is the if I ask myself this question, then x f of x comma v is first of all f of x comma v dx dv is the probability of finding a drop in the size x to x plus dx. So, if x is the size, then the probability multiplied by the size added over all the limit, okay, gives me a differential probability of all the drops in the range x to x plus. So, this is now all the drops, but having velocities v to v plus dv. Okay, now, this is really, this dg is a probability. Because I have taken the probability of the f of x comma v dx dv is a probability, then I have taken all the probabilities and added them up, but I have not added up all the possible probabilities over all the range of v going minus infinity to infinity. So, dg is basically a probability of finding a drop of any size, okay, of any size. Let us do one thing, we will even erase this x. So, just to get our argument straight with the probability part, and then we will look at the mean part. So, if f of x comma v dx, and if I am only integrating in the limits over x, that is giving me a differential probability of finding a drop in the range v to v plus dv. Okay. So, let us first define that. So, this dg d over dv is integral 0 to infinity f of x comma v dx. This is the velocity probability density function. So, what we have on the right hand side here is only a function of velocity. So, I will call this some h as a function of v. H is a velocity PDF. Why is it? It is not just a function of v, it is actually a PDF, because this is automatically satisfied. Okay, this is actually coming from our basic definition of this the integral of f of x comma v dx dv equal to 1 over both the ranges. So, if I just take this part, and if I call that some new function h, the integral still remains 1. I can likewise define another function, we will call this p of x, which is minus infinity to infinity f of x comma v dv. So, this p of x is where I have integrated out the probability in the velocity space. So, I do not care this is a mathematical statement, what it physically means is that I do not care what the velocity is, tell me what the probability is of finding a drop in the size x to x plus dx, what the probability is of finding a drop in the size x to x plus dx, and that probability divided by dx gives me the probability density. Okay, that is what this p of x is. Likewise, h of v is physically saying I do not care what the size is, just tell me what the velocity distribution looks like at some point in the spray or the whole spray. We will get to that in a little bit. Okay. So, these are in some sense two simplifications of the full f of x comma v in one coordinate or the other only. So, let us look at some real experimental data to see what this actually means. Okay, this is data that was obtained using an instrument This is experimental data at one spatial location in the spray. Now, what we see here, there is about 10,000 dots on this graph, each dot is one drop. So, this was an instrument called the PDPA. Okay. It is called the phase Doppler particle analyzer. We will look at that again later on in the class, but let us just say it is a particle counter. So, I have a way of counting every particle going through that instrument at that point and figuring out what its size is as it goes through there. So, I took a sample of 10,000 drops at one point. Typically, this may be like half a second of real time in a reasonably, we looked at these numbers, right. A simple perfume whiff has about a million plus drops. Okay, so, to sample 10,000 drops is hardly any time. So, what we did is we took the each drop, and you see each drop and its size. You can see how the size never really goes to 0. Let us say the smallest drop I know in this sample is probably about 1 micron. The largest drop is slightly less than 250 microns, actually it is slightly greater than 200 microns. You can see that is the largest drop. The smallest drop may be somewhere here. So, if I now take the probability density of this and I am going to draw it on this axis. You can see how the density is 0 at 0. The density quickly rises reaches a maximum and then in fact, since this is experimental data, it actually becomes 0. Let me just make that line a little straighter. So, if I now look at what I have essentially done is I have taken the drops, all of the drops, and from essentially creating, you can imagine a histogram first. So, I have created a histogram, and from that histogram I have constructed what looks like a continuous curve, which is my, so this is my probability density function in the drop size space. Okay. We will look at a stepwise procedure of doing this in an example as well, but for now that red curve that I have drawn on top of these blue dots, you can see sort of qualitatively indicates a density of these drops in this vertical coordinate called diameter. Okay, the vertical coordinate is like a diameter, and how densely are these drops packed in that space is this red curve is an indication of that. You can also see that it satisfies all of the general criteria we set out for an actual spray PDF, which is saying that the probability density should be nearly 0, should be 0 for drop size being 0. The probability density should tend towards 0 as the drop size becomes large. The probability density should achieve a maximum at least one point. So, for example, I could, for all I care, have more drops at another point. So, that would give me 2 peaks on the drop size distribution. That would be perfectly acceptable. It would just be called a bimodal distribution, and I could go on, and there is nothing that precludes us from having more and more maxima, but in a real spray a bimodal distribution is about as complicated as we get. Typically, a single mode, single maximum point on the PDF is what is more commonly observed. Okay. So, now if I move on to the velocity, now in this case I have not plotted the velocity, this is actually a plot of speed. Okay. The speed is slightly different from velocity, in that velocity is allowed to go from minus infinity to infinity, speed is only a positive number. So, without going into much details, you can see how if I were to draw a PDF of this, shows a graph that looks something like that. Okay. Now, we will look at functional forms of these graphs a little later on, but essentially you can see again that it is hard to find a particle that is of 0 speed, meaning there are hardly any dots near the bottom of this vertical axis. It is hard to find a very fast moving drop either. So, 30 meters per second is about as fast as this sample of drops had, but most of the drops were moving right about 10 to 12 meters per second. This is again one spray at one point, a distribution of 10,000 drops, a sample of 10,000 drops at that point. Now, if I take the size and velocity as the two independent axes now. So, look at it this way, I have the diameter on the x axis and real axial velocity now on the y axis. Believe me, there are 10,000 little triangles on this graph. So, every drop that we sampled, that we showed in the previous two graphs, where the x axis in the previous two graphs was a number called the particle number. It is like it's imagine I slap on an ID to every particle that is coming through 1 to 10,000. Okay, so, it is just like some way to distinguish from drop to drop. In this particular graph, in this graph what we have done is we have ignored the particle ID, that is I do not know when the particle came. In the previous two graphs, the ID was to show like a sequence of arrival as a matter of fact. So, let us go back to that graph and look at it a little more carefully. If I took a sample of the first 1000 drops and constructed a PDF just like this, and then took the sample of the next 1000 from 1000 to 2000. Similarly, if I constructed 10 separate PDFs, would the 10 be approximately similar or would they be totally different from each other? They are all going to look approximately similar. I can take all the drops in that little strip, or this little strip, they are all going to look approximately similar. I have about 1000 drops in every strip there, right. So, what that says is, if the PDF constructed from any point, any sample of the population is the same, I can call the spray as being stationary. That is, at least in the time that I have investigated it, which is this half a second, nothing drastically is changing over that time. I can call this spray as being statistically time stationary. That is, if I now were to extrapolate this belief that I have, all I can say is I can take a 10,000 drop sample tomorrow on the same operating condition spray, and I can expect to get a PDF that is approximately the same. It is a very important belief to have, without which you cannot do experiments, right, or for that matter go further in any fashion, right. So, this idea of stationarity, that is, if I bring on the same supply pressure, same air flow rates, etc., I can get the same spray from a PDF sense. The exact arrival times of every drop could be different, but I am not concerned to that microstructure of the spray. The macro structure in terms of this PDF, I say it is not really a macro structure, the statistical structure of this spray is repeatable. I am able to reproduce it tomorrow. Okay. Same thing if I now come here, if I throw out the timestamp or the ID and timestamp are interchangeable, right. I can look at every drop in this size. So, essentially this is x in our old description, f of x comma v. If I now construct a mound in this, if I now construct a mound in this f of x comma v space, that mound is going to be my f of is my two dimensional probability density function. In the previous graph, what we could draw as one line curve now becomes a surface. So, in this f of x comma v, you can clearly see that right about this middle region there is a real peak density, and in this little ring around here there is less of a density. So, I have a peak, essentially it is like a little hill, that is sloping away from this peak. That is going to be the nature of this f of x comma v. Now, I want you to pay close attention to one thing. The diameter scale here is logarithmic. Okay. That means, in the log of the particle size, I get what to me looks like a Gaussian curve, Gaussian or a normal distribution curve in the diameter space. The velocity coordinate here is linear. So, the f of x comma v, this is now real experimental data, right. F of x comma v tends to show a Gaussian like behavior in the log of the particle size and Gaussian like behavior in the linear in just v. Okay. So, if I were to do this, if I was to create a probability density function of this graph, essentially I can see this is my p of x from the previous graph. The probability, this is my f of x comma v, so these dots in some sense, if I was to process them appropriately, I will get f of x comma v. If I ignore the velocity coordinate and only do the binning in the x coordinate, what I get will look like that top red curve, that is my p of x. If I ignore the diameter coordinate and only do the binning in the velocity coordinate, you can see how I will sort of get something that looks like this. This is my h of v. So, this is a graphical representation from a real data set of what p of x is, what h of v is and what f of x comma v is. Okay. Now, when can I say that there is no size velocity correlation in this data set? Okay. That is a physical question to ask, and there are mathematical implications associated with it. If all of these points that you see in this graph are sort of oriented along the coordinates, meaning if I was to draw a best fit straight line and different levels of confidence interval on that best fit straight line. If the straight line is going to be a horizontal line, okay, if the best fit